So continuing on in this video, Lee is going to, what, test out the test framework?
Yeah. Well, the other video was getting kind of long, so I wanted to cut it off
Fair
in
enough.
case when we hit the build and run button, something explodes.
I gotcha.
So let's. It looks like I've got everything in there. Let's go ahead and hit F5 to build and run this and see what we've got. So, all right, it took 2 milliseconds to run through 100 iterations. Yeah, see, look, I misspelled the iteration.
I wasn't going to say anything.
And then our min value is at 0.01, so not quite 0, and 0.98, not quite 1. And we've got our distributions here. I'm going to go back and clean this up in a little bit too. So you can see that 0 to 1, we've got 10, 1 to 2, 11. But then we get down here to 0.6, or 0.6 to 0.7, we've only got 6 values in here. And then 0.9 to 0.9 to 1 is only 6.
Wow, so this thing is more heavy on the 0 to 0.5 side.
Yes. So the first part of it, so the first half is heavy biased to here. And then if you look here, 0.2 to 0.3 is 14. Now, this is called a zero biased problem. Some number generators for the first, X number of iterations, after they first get seeded, before they start getting filled in, if you seed with a low number that has lots of zeros in their bits, the numbers will be biased towards 0. And then eventually, as you start running more and more iterations, we'll see a more equal distribution, and our mean or average will ideally this should be 0.5, but right now we're under 0.5. But as we start taking our iteration counts coming up, we'll see that our distributions balance out, and we'll also see our average balance out as well. So I'm going to go ahead and close this one, go ahead and fix those things real quick. So mostly typos there. Distribution there. Now let's go ahead and take our count and we'll double it. We'll start off small and then we'll get up into larger numbers. Run it again. All right. First thing you notice, average 0.49. We're starting the balance out. If you look at our other numbers, we've only just doubled our iterations, but our balance is the balance between our distribution is starting to balance out.
Very fascinating. This is just stuff I've never stopped to think about before. It's very cool.
So, and we're still at 0.01, but we're starting to approach 1 a lot closer. So let's go ahead and kill that. Let's jump our next step to 1,000 numbers. All right, so we've hit real close to 0.5. We're much closer to 0, and we're still pretty close to 1, but not quite there.
Yeah, but we're real close to it.
Right, and our distributions are still fairly even. It looks like we've got a just under 20 or 17 number spread across it. So what you'll find as these number of iterations get bigger, everything approaches and steadies out. That's a hallmark of a decent number generator. So this one,
look at that. Awesome.
So now we're getting even closer to 0.5. Our approximation to 0 is really, really close. 1 is getting incredibly close as well. So things are steadying out. But notice it took 100,000 iterations to get really, really accurate, because this is, again, random numbers. You're not going to get a perfect spread, but the closer these numbers get over the less iterations, the higher quality of a generator that you have. Now, the one thing that I don't know, though, here is the size of the period of the sequence of numbers. I don't know how many numbers it can generate before it starts iterating. But at 100,000,
before it starts iterating, or before it starts repeating?
Before it starts repeating.
Okay.
Where the entire sequence of numbers repeats over again.
Right.
But if you look at our duplicates, we've got 2 duplicates. That's not too bad at 100,000 iterations. Definitely not repeating. That's another problem that, or with not knowing the algorithm that's being used exactly, or knowing the statistic of how many numbers can I use before I start repeating the same numbers over and over again, getting through the sequence. So with using a known algorithm that that we know and implement, we can go, okay, I know that the well 512 has a period of 2 to the 512. So that gives us that little ability. Also, look, we're still at 13 milliseconds for 100,000 iterations. This thing is incredibly fast. Let's go to a million. 170 milliseconds. And we're starting to even out quite nicely throughout the range. We're still at 0.5, very close to, very close to 1 and very close to 0. Not exactly, but very, very close.
Right.
And 231 duplicates. Now, I don't want to go much farther than, I can go up to about 36 million, I think is the largest I can go before my machine runs out of memory. This is on your machine, so I have no idea what I can go to. So let's just do, let's go there, 50 million. Let's see if I can blow your computer up too. Yep, I can blow your computer up. Okay, that answers my question. But so let's drop back down to 4 million.
40 million?
No, 4 million.
Oh, was it? Yeah, it sure was.
Yep. So everything starts balancing out. So the trend is the more numbers that you're getting, the more accurate representation you're getting because you've had more chances of going through. But at 4 million, we're at 3,600.
Yeah, boy, they're really
numbers.
Jumping up there.
Yeah, this is exponential.
Yeah, I see that.
The larger these numbers, these get larger and larger. But what I wanted to do in this video is basically test out the framework, fix any spacing, spelling issues that we've got, and then show you what these numbers mean and how we're going to use those to evaluate the algorithms that we come up with. By using a known working algorithm, we can go, okay, so this is the trend we can expect. So if our algorithms are running roughly at the same speed and we're getting the same distributions and our means are about the same, then we know we've got a good algorithm. If our duplicates are more, not so good. If our duplicates are less, even better. So it's a lot of trade-offs. And just kind of a side note, 4 million iterations on your machine took less than a second. This takes about 4 seconds on my machine.
Seriously?
Yeah,
wow.
4 to 7 seconds on my machine.
Wow. So yeah, this new processor is definitely pretty mean.
Yeah, I was looking at it, I was going, wow.
That's incredible.
Yeah, your machine is really, really screaming fast.
Wow, I see that.
But that's, like I said, this is just a framework so you can play around with number generators and test it. Because once I show you these, particularly the hashes, not so much the well 512. The well 512 is based off of a proven algorithm. The hashes that we're going to be using are for a very specific function, and those are kind of hand-rolled by me. So changing some variables here and there may get you better or worse results, and feel free to go ahead and play with those or swap stuff out. That's pretty much what I did for an entire day, was ripping these algorithms apart, seeing what I could change, how it affected the spread of numbers and the mins and maxes and the time, just so I could get the best results I could get. The results I cared about the most was how many iterations could I get in the smallest amount of time with the least amount of duplicates. And then secondary, I was looking at trying to get a mean that was at close to 0.5 that had an even distribution. So the mean, the distribution was secondary to the fact that I wanted something that ran fast with as little duplications as I could get. And we'll see with the hash that I came up with Vice, the hash that we started off with. We've got a huge improvement, but we're still nowhere near this type of number. The well 512 will blow this one away.
Awesome.
So the well 512
And speed-wise?
runs a little bit slower, but we have better distribution.
Mm-hmm.
And I think at 4 million, it's like 200 and some duplicates.
Wow. Very nice.
So,
all right. Well, is that pretty much everything we wanted to cover here in this video?
right, for the this video and the next video, we'll start off with our very first generator, which is in truth a hash.
Okay. All right. Well, with that, we'll wrap up this video. Thanks a lot, everyone.